Good morning, students. Okay, we will start the class. Wait a second. So, we will discuss the last unit's topic, that is analysis. So, let's start the class. Let me first share the screen. So, the last topic was here, this one, the analysis of dual pulse converter. All of that, all of the previous has completed. So, this is the topic that we are discussing today in today's class. So here it is written. Here first you must see this diagram. Okay. Here we have taken the three induced EMF on the source of supply, that is EA, EP, and EC. Having current flowing through each of them is your EA, EP, and EC respectively, and the inductor is connected through each of the across each of the voltage source. That is I. This is the current flowing through this one is IS, the IPS, and this is named as ICS. Now, all these are connected between another form, that is IAT, IPT, and ICT. All these are connected through another inductor that is named as IAD, IBD, and ICD. Another in the parallel connection or in the same approximate circuit diagram, you can say the bridge is also converted with the this inductor form. Okay, and the overall voltage, these two voltage are connected in series. All these are connected in series, so that the equivalent voltage, that the output DC voltage is taken as VD1 plus VD2, and the current flowing through the HVDC link or the current sources are given as ID. Now, this is called LD, is your smoother reactor. Okay. Now here you can see the 12 pulse converter circuit is obtained by two 6 pulse converter connected. By two 6 pulse converter connected in series. As you can say, when two 6 pulse converters are connected in series, then it form a 12 pulse converter. Okay, it has been shown in this diagram. This is your 6 pulse converter 1, and this is your another 6 pulse converter 2. Only we have taken the single, so three sources, that is identical sources for both the converter. When you combine both the converters in series, both the 6 pulse converter in series, then it will be accumulated as your 12 pulse converter. Okay, so here you can say this is your 6 1 and this is your 6 1, this is 12. So this is the connection of star to star connection. This is called star to delta connection. Okay, so here you can see that the plus negative plus negative plus negative is connected with each other. So the diagram specification is given. When two 6 pulse converters are connected in series, then it form a 12 pulse converter. Okay. Now, the figure shows two transformers with the primary winding connected in star and connected to the common supply. These two are transformers are connected in the first one star to star connection, and second one is star to delta connection. Now, the current flowing through this converter station is given as IA, that is total current. This is the total current, that is IAS plus IAD. Okay, here you can say at this node, this IA is divided into two parts. First one is going in the rightward side, and another one is going in the downward side. So we can add at this node as IA equal to IAS plus IAD. Similarly, for the current flowing through the B section, that is IB equal to IBS plus IB. So all the current is given here. IA plus IA, IB, and IC is given. So it is written in determining voltage and current waveform. Let us assume no loss. That is ideal case. And turns ratio of the transformer fed up bridge is bridge 1 as 1:1. That is, you can say this is isolated transfer. We just isolate the one circuit from another. This is the ideal case we have taken. And turns ratio of the transformer fitting bridge 2. And for the second one, that is star to delta connection, the turns ratio is 1:3. 1 is to root 3. Okay, so we have taken 1:root 3. That means primary number of turns is root 3 times of the secondary number of turns. So the phase voltage of 12 pulse converter station is given as here you can see that here you can see let the phase voltage of 12 pulse converter. phase voltages. We have taken the phase voltage E equal to under root 2 upon 3 EL. This is the line voltage between the converter and the transformer. This is the line voltage. When you relate this line voltage with the phase voltage, this is given as by this format. Here the phase angle is taken as 150 degree in the leading case. In the leading case, we have taken 150 degree. Similarly, if it is displaced by 120 degree, the second one will be at 30 degree and the third one will be at minus 90 degree. So accordingly, the phase voltage of each source of supply is given here. That is EA, EP, and EC is written here. Now all these, the first one is converted into star connected, and the secondary is the phase voltage given by this format. That is ES for this value. For the ES, here you can say that the voltage developed across in the first bridge is given as EAS, first one. Then second one is EBS. The potential between both of these is EABS, that is given as EABS. Similarly, for the second and third one, it can be written as EBCS. And for the third one, you will get ECAS. The similar case occurs for the here. EAS given as under root 2 upon 3 EL sine omega t dash, which is the difference of the first potential, first EMF to the second EMF. That will give you the value of the ES in the format. Here it already told EABS. EABS is the difference of the potential between EA and EB. So EA minus EB equal to under root EL sine omega t plus 180 degree. EBCS is given as EB minus EC equal to root 2 EL sine omega t plus 60 degree. Then ACS, you can write ACS or CS depending upon which one is the higher value. So we have taken EA has a higher value than EC, so it is written EACS as EA minus EC, and the formula is written as it is. So here also the phase angle displacement is your of 120 degree. So it is written 180 degree, the minus 120 to 120, you will get 60 degree, again minus 120, you will get minus 160. So in equivalent, when the line voltage and phase voltage is related, these are given as line voltage equal to phase voltage into root 3. That is the condition of star connection. Now, this is all about for the star connection. Now, what about the delta connection? So for the delta connection, the turns ratio, or you can say as this one is a star to a star connection, so the conversion has been done. In the second format, this is a star to delta connection. So it is taken here for the star to delta connection. The ratio is 1:3. As we have taken the transformation, turns ratio is taken as 1:3. So the line voltage to phase voltage, when you relate line voltage to phase voltage, you will get this as EABT for the second transformer, as you can see from here. This is the second for star to delta connection. It is connected with your IAD, IBD, and ICD. Here also the current with the suffix small a, AD, BD, and CD is given. Now the potential across is the, let us say this is your EA, EB, and EC is given here also similar to the previous one. So here also we have taken EABD root 3 EA. Then again EABD is given as root 2 EL sine omega t plus 150 degree. That 150 degree you can take from here, or you can say from here you will get. So accordingly, we have put in the value of EABD, EBCD, and ECD. Okay. Now here you can say root 3 is the multiplication with EABD. So when you multiply root 2 upon root 3 with the root 3 will be cancelled, so that it will get the value EABD equal to root 2 EL sine omega t plus 150 degree. Okay. Now the comparing the equations 7, 8, 9, 10, 11, 12. That means this you can compare this value and this value, a 7, 8, 9, 7, 8, 9 equation and the 10, 11, 12 equation. We can see that the node, the voltage applied to the bridge 2 has phase difference. That is, you can say, let us say EABS is your omega t plus 180 degree. Here it is EABD is omega t plus 150 degree. So that you can see that the phase voltage difference between this one, 7th equation, and the 10th equation is 30 degree. It is at 180 degree and it is at 150 degree. So the phase difference is your 30 degree. Similar case occurs for the other person. That is what written here. So you can see here the voltage applied to the bridge 2 has phase difference of 30 degree to the voltage applied to bridge 1. Thus the bulb 3 in second bridge will be fired 30 degree after the bulb 3 in bridge 1 is fired. Okay. So you can see this is the bridge 1. As you can see, this is the bridge 1, this is the bridge 2. If you compare this equation, the first equation that comes from the star to star connection, the second three equations comes from star to delta calculation, you will get noted that the phase difference is 30 degrees. So if any bulb fires from this bridge one, then for the firing of the firing angle for the bridge two is at 30-degree delay, or you can say after 30-degree delay, the second three-phase equation, three bridges will fire the voltage that is written in the theoretical format. We note that the voltage applied to bridge 2 has phase difference of 30 degree to the voltage applied to bridge 1. Thus, the bulb 3 in second bridge will be fired 30 degree after the bulb 3 in bridge 1 is fired. Okay, that is the case. Now, here you can say the 12 pulse converter has 12 pulses of output. That is 12 pulse converter has 12 as we have studied in 6 pulse converter, we had 6 out pulses output. Here it is 12 pulse converter has 12 pulses of output with each duration of 30 degree. Okay. Thus, the transformers are connected as star to star and star to delta that we have discussed in bridge 1 and bridge 2, respectively, to obtain the output of the terminal. The output of the terminal is given in this format. This is a VDC, that is which terminal or which voltage potential difference is applied across the bulb equation. So here it is written bulb 1 and bulb 2, that is the interval, that is what is the function of the interval. IA and IB is given. The bulb conducting in bridge 1 is given as 2, 3, and the voltage developed across first 6 pulse converter is EBS, and for the conduction in the second part, only the first one is 1 and 2, and here the voltage developed is ECD. So the accordingly the format you can see that for the different value of the conduction of the bridges, the development of the voltage across the each potential is quite different. All the balls are conducting. Here you can say 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, and again 6 to 1, and again 1 to 3. So if you consider here it is at 150 degree, then for the second one this will be at 60 degree phase difference, then again 90 degree phase difference, then 120 180. Accordingly, when you start in clockwise rotation, you will get from 0 degree to 360 degree, and after 360 again the bulb 1 and 2 will start conducting. Okay, this is the function of the phase difference of the function between 12 pulse converter, 12 pulse bridge converter. Now the average DC voltage is given by this. It is written average DC voltage, as you know, the voltage developed across bridge 1. When you combine with the voltage developed across the bridge 2, you will get the total voltage developed across the your HVDC link. So for that value, we have taken the equation VD equal to VD1 plus VD2. Now here it is written VD1 have the value EBCS and secondary, and VD2 is for EAC for the second bridge converter. Now put the value of EBCS that we have derived. Here you can say EBCS is here. You can say EBCS is EP minus AC, and the equation is this one. And the equation is this one. So put the value of EBCS, you will get this one. EBCS, you will get root 2 EL sine omega t plus 60. Again, for the value of EACT, you have to put the accordingly the equation. Now, root 2 EL is the common term in both equations. So we have taken out from the parenthesis, and you will get sine A plus B minus sine A minus B. From there, you will use the geometric equation, that is sine A plus sine A plus sine B, you will get 2 sine A plus B. From accordingly, you will get the value 2 sine A plus B divided by 2 into cos A minus B divided by 2. And as you know, sine 90 degree minus theta equal to sine 90 degree plus theta. So from accordingly, we have used this geometric trigonometric equation to solve this equation, and you will get VD equal to root 2 EL 2 sine omega t plus 75 degree and cos 15 degree. That means if you compare, or if you write in proper term, you will get 2 root 2 EL cos 15 degree sine omega t plus 75 degree. That is the average DC output voltage. This is the average DC output voltage that you are getting from the 12 pulse bridge converter. Now here you can say that what is the average output voltage? Average output voltage, the proper average output voltage is taken by this equation by using the your time duration function. That is when as the your second 6 pulse converter is at 30 degree delayed of firing angle, you will get the difference of the angle between limit from alpha to alpha plus 30 degree. That means if you take a reference as alpha equal to 0 degree, then at the second function or the second converter, that is start delta bridge converter, that is advancing or delaying by 30 degree. That's why we have taken alpha plus 30 degree. So accordingly, use the formula this one, that is 1 upon pi by 6, pi by 6 for 30 degree, and range is alpha to alpha plus 30 degree. Use the value of Vd, you will get your d omega t. So with respect to d omega t, you have to integrate. So 2 root t, 2 root 2 el sine omega t plus 75 cos omega t. That means just put the value of Vd in here. You will get the equation. That means 1 upon pi by 6, 2 root 2 el. That is the constant term. So take out this whole term. You will get cos 15 degree is also constant. So we have taken out the constant cos 15 degree. Only d omega, the term related with omega t is kept inside the integration form. That is alpha to alpha plus 30 degree. Sine have omega t value. So we have taken sine omega t plus 75 d omega t. Just using the integration form, finite integration, you will get this equation, and accordingly solve by solving the above formulas, you will get the value for the two bridges. You will get BD1 plus BD2, that is EBCS plus ECD. Okay, this one is the repeated. So I'm sorry. Now, by solving this, you will get this equation. Final VD equal to 2 into VD naught cos alpha. As you know, VD naught is 3 to 2 pi EL, and EL is the line voltage between the transformer and the bridge converter. So the average DC output voltage is given by this one. This is the initial voltage. This is the output initial voltage. This is the angle of rectification, or you can say pi angle cos alpha, and the average output voltage is given as Vd equal to 2 Vd naught cos alpha. Thus, the output of one bridge is Vd naught cos alpha. That is the bridge connected in series given as Vd plus Vd1 plus Vd2. That means Vd naught cos alpha plus cos alpha, you will get 2 Vd naught cos alpha. Either you can use this equation, or you can use both, will have the same output. That is Vd equal to 2 Vd naught cos alpha. Okay. Now, what about the AC current harmonics? What about the AC current harmonics? So this is the average DC voltage that we have discussed and derived. So if you have any problem, then ping me on the WhatsApp or mail me. Otherwise, you should do the formulation part or derivation part by yourself, as we have discussed already. So in the next topic, we were going to study about AC current harmonics. AC current harmonics. As harmonics already know, harmonics is the basic term related with your signal system. That is when non-sinusoidal function is converted into sinusoidal, when non-sinusoidal waveform is converted into sinusoidal function, and when that sinusoidal function, when conversion at the, when the exponential of the power of the exponential is in multiplication of some integer, then that term is related with your harmonics. Okay, so this is the AC current harmonics. We were going to discuss about AC current harmonics. So wait for just 1 minute. We will start this AC current harmonics. So let's start the class. So let's start the topic, that is your AC current harmonics. Now you can see the current in IBD. Here, this is the delta formation. So the current flowing through this one is, first one is, this one is I1, this one is I2, and this one is I3. That is moving in anti-clockwise direction. The current is outward. That is IAD, IBD, and ICD is taken. Now the AC, for about the AC current harmonics, it is given the current IBD flowing in the primary winding of the star delta transformer is given as by this equation. As you can say, IBD is root 3 into I2. Okay, that is the phase current, and line current is taken here. Okay, the line current is always root 3 times of the phase current for the delta connection. So here it is given as the transformers ratio is 1:3. That is for the star to delta connection. That is the second 6 bridge converter. So current also, so the current will also be in ratio of the 1:3. That it can be written as IBD is 1 upon root 3 IBD minus ICD. So this is IAD, IBD, and this is ICD. So we are considering these two terms, IBD and ICD. So at this node, you can say I3 is leaving the node, I2 is coming towards the node, and IBD is also leaving towards the node. So from there, you will get IBD plus I3 equal to I2. So put the value of similar kind of things occurs for this ICD. This is the current ICD, and current ICD is for this node. You can say ICD is leaving this node, I2 is also leaving this node, and I1 is coming towards the node, this node. That means ICD plus I2, that will give you the value of I1. So accordingly, if you apply the KCL, you just have to write the value of this IBD. IBD is your I3 minus I2, that is I2 is coming, so and IBD is going away from, so you can say I2 minus I3. Similar kind of occurs for the ICD, that is I2 minus I1 plus I2, that is your value will be I1 minus I2. Accordingly, if you minus, then you will get minus I1 plus I2. So this I2 and this I2 will become 2I2, and I3 and I will, you will solve, you will get 3I2. Okay, 3I2 means I, for this I3 I1, you will get at this node, or you can say this is the summation I1 plus I3 plus I2, you will get equal to 0. That means I1 I2 equal to minus I1 I3. So accordingly, if you put the value, you will get 3I2. Okay, like now solving this equation, you will get root 3 into I2. So IBD have the value root 3 into I2. This is the IBD, root 3 into I2, that is coming. Similar kind of IAD will be root 3 into I3, and similar ICD equal to root 3 into I1. So accordingly, by using the equation, you will get IBD equal to 1 by root 3. I2 is your, this is your I2. I2 is your IBD minus ICD. So just put the value of their IBD minus ICD. So accordingly, you will get the value of IBD. Now here you can say the nature of the waveform, that is IBP and ICD, are same. So the nature of the waveform is just like a staircase, and you can see the value of the current flowing through this delta star to delta connection is taken here. Now the angle of projection, that is angle of firing angle, depends upon the IBC, ICD, and I is given. So here we have started from 180 degree, the angle, the current is 9 lagging. Now you can say negative current is flowing up to minus 120 degree. From 120 degree or 60 degree, you will get again this function. Again this function you will get on the downward. So accordingly, if you draw this waveform in the angle projection, you will get this the positive value of the theta. You will get after your value, you will get 2.515 R 154 ID, similar 15777 ID, and accordingly the current is deteriorating, that is decreasing the value as the theta is increasing. So accordingly, if you solve the equation, you will get this. Here it is written the waveform, the IBS, IBD, and IBD are shown. Okay, this is the given. So it can be shown the RMS value of the fundamental component of the supply current in a 12 pulse converter is given by this equation, that is T1 equal to root 2 root 6 pi upon pi into ID. Now the harmonic component that is flowing in the current is given by this equation, IH equal to I1 divided by H. Now the here the value of h is given for the 12n plus minus 1, where n is an integer, or 6m plus minus 1 when m is an even integer. So here you can say n is for any integer, and whenever the m has the even integer, you will use this value 6m plus minus 1. Okay, now accordingly, if you draw this diagram, you will get this one. This is the explanation. This is the explanation part, the whole diagram of the bridge, and this is the small portion, so that you can understand the value for the value of IAD or IBD. That is the value of 2 root 3 ID, 1 upon root 3 ID, and the angle is 30 degree to 90 degree. For 30 degree to 90 degree, the value of the current is given. Now, for the convenience of the overdue, axis is chosen such that the waveform have even symmetry. Okay, the symmetry should be there in the choosing the value of the this equation, this uh, uh, this value. Okay, this one. Okay, accordingly, the when you solve this equation, when you observe this diagram, you will get this equation as I1, that is summation for the n, that is for the in the Fourier series term. That harmonics, basically, as we have discussed, this is the basically a signal system process. So you can say IA1 is the summation of the n terms for this equation, an1 cos n omega t. That is, first one is your cosine angle in terms of cos value. So put the value of an1, that is your coefficient of the cosine value. So you will get 2 upon pi by 2, that is 4 upon pi. And accordingly, if you have the value of n number of turns, then you multiply n. Just put the value of that IA1, that is ID root 3, with the range from 0 to pi root 3. As you can say, this is 2 upon root 3 ID, 0 to 30 degree, or you can say 0 to 2 pi with 3. So put the value of that, that is 2 upon ID, you will get this equation, that is 4 ID upon n pi. Then this integration of cos omega t is your sin omega t, and the range is from 0 to 60 degrees. So we have taken 0 to 60 degrees. Just put the value of at omega t as pi by 3, as sin 0 at the value 0. So the value of n0, an1 will be 0 for n not equal to k. Now for n equal to 6k minus 1, you have the value minus 2 of root 3 upon n pi into id. Just when you put the value of n, you will get this equation. And for the positive, for the negative integer value, or if you have the value of, let us say, this is your k equal to 0, k equal to 0, or we can say minimum value 1. We have taken 1. That means this will value of 5 minimum value. And if you are taken as k equal to 1, you have the value of let us say 7. For the minimum value of 5 is your minus 2 root 3 upon n pi into id. Okay, now this will be n equal to 7. Just put the value of n equal to 7 here. You will get 2 root 3 id upon 7 pi. So here the k is an integer value. See, as we have discussed, this one IA1 similar kind of occurs for parallelly. IA2 will be taken. So accordingly, if you combine IA plus IA1 plus IA2, you will get the total current flowing in the bridge. So here we have taken IA2 in terms of, again, the coefficient is given for AN2, and the range is from the n number of turns and the cos omega t. Now the AN2 must be derived according to this formula. That is, AN2 is given by 2 upon 4 upon pi divided by n into id, and the range is from 0 to pi by 6. As you can say, this is your 0 to 90 degree. It is divided into 1 half, 0 to 60, 30 degree, and again 30 degree to 90 degree. So here we have taken 0 to 30 degree, that is pi by 6. The value is 2 upon root 3 id cos n omega t, and another one is pi by 6 to pi by 2, that is 30 degree to 90 degree. The value is 1 upon root 3 I to cos n omega t. So accordingly, just use that integration formula. You will get this finally, this equation. An2 is your 0 for n equal to 3k. That is for odd number of turns, or you can say for 3k value. Or okay, now for the value of when n equal to 6k minus 1. Now this will be for when you take, this will be positive for the k value when k is odd. This will be positive for k is odd, and negative for when k is even. So accordingly, the value of positive and negatives accordingly put up here. Now you can say for the another term minus upon minus plus 2 root 3 n pi id for n equal to 6k plus 1, where negative is for k equal to odd and positive term for k equal to n. So the total current flowing through the 12 pulse bridge converter is given by this equation. That is IA equal to, make the summation of the IA1 plus IA2. You will get this equation. You will get this equation. Now use the mathematical expression. The total current, that is I, fundamental current flowing through the RMS value of the fundamental. So in the next class, we will study this equation, characteristics of the 6 pulse converter. So this is all about today's class. Thank you.